Okay, so concept 7 is all about normal distribution. My papers are a little different because they're not back to back, but they're all the same ones that you have. So just follow along with me as best as you can. So the first thing we have is vocabulary. So normal curves are used in many situations to estimate probabilities. The pattern in the data form is a bell-shaped curve called a normal curve. So a normal distribution is our first vocab. Shows data that may vary randomly from the mean in the pattern of a bell-shaped curve. So it looks like this down at the bottom. That's called a normal distribution. Okay? All right, so the next one is a standard normal curve. Normal curve. Okay? That's a normal distribution centered on the y-axis. The mean of the standard normal curve is 0. Y-axis, 0, makes sense. The standard deviation is 1, characteristics of the normal curve. So this standard normal curve has these things. The maximum value of the curve occurs at the mean, usually symbolized as mu. This is the Greek letter mu, and we'll just pronounce it like Mew. Like if you like Pokemon, there's Mewtwo. Just cut out the 2 and just it's mu. Okay? And that's usually put right here in the middle. Okay? The standard deviation of sigma, we're still using sigma as our standard deviation. Okay? Nearly all of the area under the curve, which we're going to say 99.7%, is within 3 standard deviations from the mean. And we're going to call it like this: mu plus or minus 3 sigma. Okay, so that's a sigma. So nearly all of the data within a normal curve, 99.7% of it is within 3 standard deviations. So if we look down here, here's our mean, here's within 1 standard deviation, within 2 standard deviations, within 3 standard deviations. So the area under this curve, all of the people who fit underneath here, that's 99.7% of the population that was polled. Okay, so this is all their data, 99.7%. Okay, the total area under the normal curve is always 1, which makes sense. Okay, the area under the curve between 2 x values corresponds to the probability that x is between those values. So if I went between 0 and 1, there is a probability of people being between the mean and 1 standard deviation away from the mean. Okay, and here's how we're going to split this up. And you're going to have this on your test, but I'll put it on the board for you, but you still need to write it down. Okay, so if 99.7% of your data is between +3 and -3, that means 0.3% exists outside of 3 standard deviations. Okay. And a standard normal curve is always symmetrical, so if you have some percent of data over here, you're going to have the same percent of data over here. So if 99.7% is between -3 and +3, then 0.3% lies outside of it, and if it's split in half, that means outside of +3, there's 0.15% data that's outside there. Or there's a 0.15% chance that somebody lies outside of those standard deviations. And hopefully that makes sense. I mean, you know, if 99.7% is between -3 and +3 and it's even, then half of 0.3% lies outside on each side. So, I mean, it makes sense. Okay, between 2 standard deviations and 3 standard deviations is 2.35% on both sides. Okay, so remember it's always symmetrical. Between 1 standard deviation and 2 standard deviations is 13.5%. Again, that's on both sides. Okay. And then right here in the middle, 34% of your data is going to be between 0 and 1 standard deviation away in either direction. Okay. So we'll visit this a little bit more later. Okay. So we're just going to come over here. Using a normal curve to estimate probabilities. So this bar chart thing is called a histogram. Maybe you've seen one before. We've made some in algebra before. It's just a fancy way of saying a bar chart. Okay, so that's a histogram. So this histogram says these are the heights of men between the ages of 26 and 35. These are their heights in inches. This is the percent of them that have that height. Okay, so we're actually going to write down the percent of each one using this chart. So it looks like men who are 64 inches tall, which is 5'4", is about 1%. So we're just going to write 1. If we go on in the next one, it looks like people who are 65 is about 3%, maybe. 66 and 67 look about the same. We'll say they're both 6%. Okay, so I'm just looking across and finding the percent. So like this guy here, if you want, you can use a ruler to help you see. So like this guy looks about 11%. Okay, so it's like right smack dab between 10 and 12. This one here, maybe like 13%. Okay. Sometimes a ruler is helpful to see. This one up here, we'll say 16. Okay. This one here, not quite 15, so maybe like 14.5. This one, 12. This one here, 8. This one, 6. This one here, not quite 3, maybe like 2.5. And then this one, maybe like 1. So if you want, you can add all these up. I've done this already, so these all add up to 100%, which, as it should. Okay, so example number 1. In a survey of American men, the heights are distributed normally about the mean as shown in the graph above. About what percent of men aged 26 to 35 are 68 to 70 inches tall? So we're going to go 68 to 70. So we're just going to add up 11, 13, and 16. And that will give us our percent, which is 40%. So using a histogram is really easy because you just have to look and see what percent, and then you just add them up. Okay? About what percent of the men in the survey are less than 70 inches tall? So not including 70. So we're going to go less than 70 this way. So we're just going to add up all these percents here. So we have 13 plus 11 plus 6 plus 6 plus 3 plus 1. So 13 plus 11 is 24, 30, 36, 30, oh, you can't see that. 24, 30, 36, 39, 40. Oh, another 40%. Interesting. Okay. Suppose this survey was the data on 1,500 men. About how many men would you expect to be 68 to 70 inches tall? Well, we know, based up here, that 40% of the men are between 68 and 70 inches. So if we had 1,500 men, all we have to do is take 1,500, multiply it by 40%, which is 0.40. Plug that in your calculator, and I'll bring up the calculator just so you can see it. Okay, so bring up the calculator and you get times 0.4, 600 men. Maybe you can't see that, but it says 600 men. Okay, we'll say 600 men. All right, and yeah, we'll do this one too. The mean of the data is 70. The standard deviation is 2.5. About what percent of the men are within 1 standard deviation of the mean in height? Okay, so we're going to go 1 standard deviation up and then 1 standard deviation back. So if our mean is 70, we're going to go 70 plus 2.5, which is 72.5. And then we're going to go 70 minus 2.5, which is 67.5. And we're going to look how many men are between these two heights using our chart. So there is no 0.5, so we're going to go 68 to 72. So 68 to 72, so we're going to go 11 plus 13 plus 16 plus 14.5 plus 12. So I wrote that all down here. 11 plus 13 plus 16 plus 14.5 plus 12. And you just add those all up, and you should get 66.5%. Okay? So that's using a histogram to estimate percentages. All right, let's move on to the next page. Hopefully that makes sense. Okay. The table below, so sketching a normal curve, this is actually pretty easy. The table below shows the lengths in feet of 40 great white sharks from Scuba News magazine. Here they are, 40 lengths. Enter these data items into your calculator and make a histogram. We're not going to do that. That takes way too long. So they did it for us already. So there we go. And it says calculate the one variable statistics. So they made a histogram. There it is. It's lovely. The one variable statistics are the mean and the standard deviation. Okay. So in this example, the mean right here is x bar is 15.6. We'll say 15.7. Okay, and then the standard deviation is right here, 2.5, we'll say 2.5. So they give us all the information we need. Okay, so sketch a normal curve showing the frequency of the shark lengths. Label the x-axis at values 1, 2, and 3 standard deviations from the mean. So here's what we're going to do. So our mean for this one is our x bar, which is 15.7. And we're just going to add one standard deviation again and again to go up, and then we're going to subtract it over and over again to go this way. So if I add 15.7 plus 2.5, I'm going to get 18.2. Okay, and if I do it again, I'm going to go 20.7. So this is pretty easy stuff. You're just adding these together. Okay, and then 23.2. And then we're going to go back this way. If I subtract 2.5 from 15.7, I get 13.2. If I subtract it again, 10.7. If I subtract it again, 8.2. Okay, so there's our mean and our standard deviations. So we're going to draw little like vertical lines. I guess I could use a ruler. Going up to separate each little section. You don't have to use a ruler if you don't want to. Okay. So we're going to count up here using this data, so I'll zoom out so you can see how many values fall within each interval. That's the fun part. We're going to go through all 40 values and figure out which ones fall within each interval. Okay, so we're going to look and see how many values fall between 8.2 and 10.7, not including 10.7. So let's look and see. I only see one, 9.4, so 1. Okay, and once we're done, we can cross it off. So how many values fall between 10.7 and 13.2, not including 13.2? So let's look and see. Not that one. This one. So 1, 2, 3, 4, 4. I count 4. So that was 12.3, 12.6, 12.2, and 12.1. Okay, so now we're going to look and see how many values fall between 13.2 and 15.7, including 13.2 this time. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I count 13. So you can go through and cross those off now. Okay, now we're going to look and see how many values fall between 15.7 and 18.2, including 15.7 this time, not including 18.2 though, so not this one, this one, this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. 14 values fall between those two. Okay, so now we can cross those off. Okay, now we can go 18.2 to 20.7, including 18.2 this time. So 1, 2, 3, 4, 5, 6, 7. 7 values there. Cross them off. Okay, how many values are between 20.7 and 23.2? Well, there's only one left. It's 22.8, so 1. Okay, so we can check to make sure we have 40 values here. So 5, 18, 28, 32, 39, 40. So we're good. So now we're going to draw a curve, okay? So there's about 13 here. Well, let's do this actually. 13, 14, 4, 1, 7, 1. So you're just going to connect them together and draw a little curve. It should look like a bell, sort of like that. It doesn't have to be perfect. Okay? So that's your bell curve. Sketch a normal curve, here it is, showing the frequency of the shark length. Label the x-axis at values 1, 2, and 3 standard deviations of the mean. So we did that. Mean, standard deviations away, frequency. That's it. We're all done with that. That wasn't so bad. Okay, so let's do this one. Actually, before we get to this, we're going to look at the 68, 45, or 95, 97 rule, 99.7 rule. It's called the empirical rule. Okay, so this is something that I'm going to give you during your test so you can look at it. It's basically everything we wrote down already on the front page, but here's what it says. When a data set is normally distributed, about 68% of the data fall within 1 standard deviation of the mean. About 95% of the data fall within 2 standard, so 68% of the data fall within 1 standard deviation of the mean. That's where these 34% come from. If you add them together to be within 1 standard deviation, that's 68%. Okay? 95% of the data falls within 2 standard deviations of the mean. So here's within 2, 95%. So if this is 68%, then that means there is 37 or 27% split up between these two. Okay? And then finally, in order to find the values that are 2 standard deviations away from the mean, we would find values that have a z-score of plus or minus 2, and we'll get to that in a second. Okay, so this is just saying what we already know. 68% fall within 1 standard deviation, 95% fall within 2 standard deviations, and 99.7% fall within 3 standard deviations. Okay, so this is just a piece of knowledge for you to have. So let's go back to using standard normal values. Okay, so if a random variable x is normally distributed with a mean mu and standard deviation sigma, then the standard normal value of x is z equals x minus mu over sigma. This is the same thing that we've learned. This is the z-score formula, just with mu instead of x bar. Okay, so the table shows, this table shows the approximate area under the curve for all values less than z for selected values of z. So this table here, if I have a normal curve, and I want you to draw this with me, and here's my mean in the middle, okay? Let me zoom in so you can see. And I have some z value here, so I plug in my values and I get some z-score, and it's over here. This table shows me the probability that something is less than z. So it always goes this way, okay? So that's how you're going to use the table, less than z, not more than z, but less than z. So we're going to do some examples so you can see how that works, okay? And on your test, I'm going to give you this table, so don't worry. Scores on a test are normally distributed with a mean of 76 and a standard deviation of 8. Estimate the probability that a randomly selected student scored less than 88. So before we figure this out, we need to figure out the z-score for this one. So we're going to use our formula up here, this guy. Okay. So our x value that we're testing is 88. Our mean is 76. And our standard deviation is 8. So if you do the calculations and you plug that into a calculator, you're going to get 1.5. Okay, so that's your z-score. So now you're going to find this in the table up here, 1.5. So the probability, because remember this table goes less than that value, and we want less than that value. So the probability that something is less than 1.5 is 93%. And that's how you use that table. Okay, so I'll draw a little star. So find area under the curve for all values less than 1.5. And we'll put use table, since you're going to have a table to use. Okay? So hopefully that makes sense. I mean, it's not too hard. Okay. This one's a little bit more tricky. Estimate the probability that a randomly selected student scored between 72 and 80. So we have two values we need to find the z-scores for. So let's do the first one, z1, test 72. So 72 minus 76 over 8. Well, that's negative 4. Negative 4 divided by 8 is negative 0.5. Okay. And we'll come back to the area on that one. Z2, we're going to test 80. So 80 minus 76 over 8. Well, 4 divided by 8 is positive 0.5. Okay, so let's use the table. Find negative 0.5 right there. That area is 31%, so we'll go 0.31. Okay, now find positive 0.5, 69%. Well, what are we going to do with those two values? So let's draw a picture. So if you're ever confused, draw a picture. So here's your mean, 0. We'll just say it's 0. Negative 0.5 is right here, right? And then positive 0.5 is right here. So that table tells me that the area less than negative 0.5 going this way is 0.31%. Okay? That table tells me that the area less than 0.5, which is starting here and all the way down, so all of this is 0.69. I'm only interested in between these two values. So how am I going to figure out what's in this little area here? If I know that this whole thing is 0.69 and this part is 0.31, well, to figure out this part, I'm going to subtract 0.31 from 0.69 to figure out what's left over in the middle. So 0.69 minus 0.31 gives me 0.38. So you can say to the answer, the kids who scored between 72 and 80 is about 38%. Okay? So whenever you want to find the answer between two values, you have to find the values less than the lower one, the values less than the higher one, and then subtract to figure out what's in the middle, which makes sense. Okay? Let's do the next example. This one. Is it normal or is it skewed? Okay. So while many data sets can be modeled using a normal curve, not all data is normally distributed. Sometimes the tail, this tail, is longer on one side than the other, resulting in a skewed distribution. A lot of values are over here, a lot of values are over here, okay? Sometimes it's not symmetrical. So, the heights of 24 children entering a theme park are shown below. The mean of all the children at the park is 49 inches, and the standard deviation is 6. Does the data appear to be normally distributed? Explain your reasoning. So here's what we're going to do. We're going to find, since we know the mean is 49, we're going to write that down. We're going to count all numbers around 49. We're going to count how many are above 49 and how many are less than 49. Okay, so we're going to cross out 49. There's one 49 here. And we're going to count how many numbers are above and how many are below. And that will tell us whether this data is skewed or not. Okay, so let's see. How many are more than 49? We got 1, 2, 3, 4, 5, 6, 7. Oops, I forgot this guy. 7, 8, 9, 10, 11, 12. Okay, how many are below it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's more above than below, so that means it is skewed left because there are more values. Remember, they get bigger as they go that way. So there's more values on this side than this side, so it's left skewed. Left skewed. And we could say because more values above than below. Okay, so if ever you want to test if something is skewed, you're just going to test it, how many are above it, how many are below the mean. So, and since there's more above, we know that there's more over here on this side, so that means it's left skewed. Okay, we're not going to worry about this part here. Okay, so we have one more example, and that's on the back here. Okay, this very, very last one. Okay, so in a college algebra course with 286 students in a lecture hall, the final exam scores have a mean of 67.5 and a standard deviation of 7.4. The grades on the exams are whole numbers and the grade pattern follows a normal curve. Good, so we know it's normally distributed. Sketch a normal curve, label the x-axis values at 1, 2, and 3 standard deviations away from the mean. So we know that the mean, they told us, is 67.5. They told us that the standard deviation is 7.4. So, right here in the middle, 67.5. To figure out 1, 2, and 3, we're going to add it going this way and then subtract it going this way. And I've already done that, so I've saved you some time. So 1 standard deviation away is 74.9. 2 away, 82.3. 3 away, 89.7. Okay, going the opposite way, 60.1 is 1 away, 52.7 is 2 away, and 45.3 is 3 away. So we're still going to draw our little vertical lines here. They don't have to be perfectly straight. I don't care. I'm not there anyway, so. On Monday anyway. Tuesday I'll be there. Monday I won't. Okay, so there we go. So our normal curve is going to look something like this. There it is. Eventually we're going to put in how many are between each one. Okay. So find the number of students who receive grades from 1 to 2 standard deviations above the mean. So 1 to 2, so we have, this is our mean, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. From 1 to 2 standard deviations, we know, based on, I'm going to pull this guy out, this guy, we know approximately 13.5% of data falls within 1 and 2 standard deviations. So we know 13.5% fall within there, and we know there's 286 students. So if we want to know how many students are in there, we're going to take this and multiply it by 286 because that's how many kids we have. So this as a decimal point is 0.135 times 286 because we want 13.5% of 286, okay, to figure out how many kids that is. So let's do this. 0.135 times 286 is 38.61. Well, I can't have a fraction of a student, so let's just round up to the nearest whole number. So we have approximately 39 students between 1 and 2 standard deviations, which is right here. And since we know that the normal curve is symmetrical, there's also going to be 39 students that are on the other end of the spectrum that are, they're going to be on the other end of the spectrum from 1 to 2 standard deviations below the mean. Just so that we know, because we know it's symmetrical and it forms a normal curve, whatever's up here will also be down here. So let's do the next one. How many students earned a grade below 60%? So we'll need to figure out what's the z-score for this one first of all. So z equals 60 minus, the mean is 67.5, over the standard deviation, which is 7.4, right there. So if we plug that into our calculator, we're going to get 60 minus 67.5 divided by 7.4 is negative 1.01, so we'll just say negative 1. Okay, this is where we use our table, okay, or we can use our table, this table right here. The percent of people that are below minus 1 is 16%, so we're going to use table, okay. We know that that's 16%. We want 16% of 286 students, okay, so 0.16 times 286, 45.76. So that's approximately 46 students, so we'll say approximately 46 are below negative 1, but we know that 39 are here below negative 1, which leaves 7 over here. Because we know a total of 46 are below negative 1, but we already know 39's here, so we need 7 more here. Okay, which also means there's 7 more here. Okay, so we can figure out how many's left here. So let's add up what we have. We have 39 plus 39 plus 7 plus 7, 92. We know 92 students are here, which leaves how many students left here? Well, we know there's a 286 total minus 92. So 194 are going to be split between these two. So if we divide that by 2, we can tell exactly how many kids are in each section. So 97 kids are between 1 standard deviation above the mean and then also between 1 standard deviation below the mean. Okay, so hopefully that makes sense. I might give you a test question like this where you have to figure out how many are between. Yeah. Okay, so yeah, I might give you one like that. We're not going to do letter D just because we're not going to do it. I decided we're not going to. So that's it for concept 7. If you have anything like this in your practice quiz, just cross it out. I didn't look at it. So that's it for this one.